All right, in this lesson, we are going to graph cubic functions and identify key attributes using transformations. And so the cubic parent function is x cubed, all by itself, just x cubed. And so to get some significant points, if I plug in -2 cubed is -8. -1 cubed is -1. Remember, when you raise a negative to an odd power, it stays negative. Okay, 0 cubed is just 0, 1 cubed, of course, is just 1, 2 cubed, +8. Okay, and so we see the point 0, 0, 1, 1, 2, 8. And then we also have -1, -1, -2, -8. Okay, and so to the right, this looks like a parabola that's opening up, but then to the left, it looks like a parabola opening down. So it creates an S shape. This point in the middle where it changes direction from opening up, or it's called change in concavity, is called an inflection point. It's going from concave up to concave down. And so the inflection point for the parent function is 0, 0. We can see that it crosses the x-axis at the origin, which means it also crosses the y-axis at the origin. So the x and y-intercept are the same. They are 0, 0. And then the symmetry of this graph is rotational symmetry. Okay, rotational. Instead of an axis of symmetry, we have a point of symmetry, which means if I were to rotate this graph, it would look the exact same. Okay, and so it's rotational symmetry about a point this time instead of flipping. If I were to flip this graph, it would look different. But since if I rotate it, it would look the same. That's why we have a point of symmetry instead of an axis of symmetry. The domain, it goes forever to the left, forever to the right. And so his domain is all real numbers. And it's also going forever up and forever down. And so his range is also all real numbers. So working with a cubic function, you never have to think about the domain and range. Both domain and range are all real numbers all the time, which means there is no global max or min. Okay, because it's going forever to infinity, in both directions, you can't have a max or min unless you restrict the domain, which we will do later in this lesson. Okay, and so to graph this, it's helpful to identify the pattern between the points in the parent function. And so we have the point of symmetry, the inflection point, and then the pattern goes over 1, up 1, over 1, up 7. Okay, so the x's are always going by ones, and then the pattern in the y's go 1, then 7 to get to those points. So over 1, down 1, over 1, down 7. And so if there's no stretch or compression, we'll still have that 1, 7 pattern in the y's. Okay, and so looking at example A, I can see that it's moved left 6 and up 1. That's the only thing that has happened. Left 6 and then up 1. And so that means it wants us to list here. So left 6, up 1. And so because we started at 0, 0 with the inflection point, and if we move it left 6 and then up 1, the new inflection point will be 6, 1. Okay, and so because there's no stretch or compression, I still have the over 1, up 1 point. You can kind of create that line between the points on each side of the inflection, but then we go over 1, up 7. So 1, 2, 3, 4, 5, 6, 7. Same pattern as the parent. So up to the right, and then over 1, down 1, 2, 3, 4, 5, 6, 7. Okay, and so to make that inflection point act like you're putting a parabola opening up connected to a parabola opening down. And so domain, all real numbers all the time, same with the range. Anytime you're working with a cubic function, you don't have to think about either. Okay, and so for this next one, we have quite a few transformations. We have a reflection across the x-axis. We have a vertical stretch by 2. And then we have right 3. And then down 4. Okay, and so that means my new inflection point is right 3 down 4, right 3 down 1, 2, 3, 4. So now we have the inflection point. And then a reflection across the x-axis is going to take the right side of our function, our parent function, and flip it down, and take the left side and flip it up. So because of the rotational symmetry, a reflection across the x-axis and a reflection across the y-axis will result in the same graph. Okay, either way, you know it's opening to the left. You can think of it as slope. You have a positive slope anytime you don't have a reflection. You have a negative slope anytime you do have a reflection. Okay, and so because of the reflection, I know the slope between my points would be negative. And so it'd be up to the left, down to the right. But we also have a vertical stretch by 2. And so instead of having this slope of 1 between these 3 points, the slope is now going to be 2. And so we can go up 2 over 1, and we can go 2, 1. And so it says at least 3 good points. And so we've got the 3 points. Just make sure you don't graph it actually as a line. You can treat it as a line, but you need to make the inflection. So a parabola opening up to the left, and then a parabola opening down to the right. Okay, and so here we still had a slope of 1. If you want to think of it as a slope of 1, and here we have a slope of -2. So you can kind of treat this value here as the slope between the points by the inflection point. Okay, and so now we're gonna identify some key features like the intercepts and max and min on intervals. And so that's where it's going to be helpful to have a picture is when we do that. Okay, so I want to actually skip to example 5 and 6 where we're just focusing on the intercepts. And so to find an x-intercept, you plug in 0 for y and solve. To find a y-intercept, you plug in 0 for x and just number crunch or simplify. You don't actually have to isolate the variable. And so the y-intercept is always a little bit easier. So I'll start with the y-intercept. And so we plug in x equals 0 to the function. And so 0 for the x. That would give me 0 plus 4 cubed minus 3, which is 4 cubed minus 3, which is 64 minus 3, which is 61. And so the y-intercept is 0 for the x, 61 for the y. Let's see if that highlights well. Nope. Okay, and then let's go ahead and do this next one. So for the y-intercept, same idea. You plug in 0 for the x, and then we have a lot going on here. So x is 0. And so 0 minus 3 is -3. Then we have a -3, which is +3. +3 cubed is 27 plus 4, which is 31. So our y-intercept is 0, 31. Okay, and so for the x-intercept, that's a little bit more challenging because we have to solve. And so for the x-intercept, the y is 0. And so we're putting the 0 over here. Okay, and so I like to write the actual expression x plus 4 cubed minus 3 on the left and then the equals 0 on the right, but it doesn't matter. So first step would be to add the 3 to both sides. We have to isolate the cube, kind of like when we're solving a quadratic using the square root property. Only now, to get rid of a cube, we have to cube root both sides. Okay, and you don't have the positive or negative cube root because cubic and cube root, those are called one-to-one functions. You don't have a positive negative when you apply a cube root. So just be careful, it's not the same as square root. And so we have to figure out the cube root of 3, which we'll use our calculator for. And then last step would be to subtract 4. Okay, and so if you don't have a calculator, you would just leave your answer as cube root of 3 minus 4. If you do have a calculator, you would just use the cube root. And to get to a cube root, you use math 4. Math 4 gives you a cube root. So math, and then option 4, you'll see it, is your cube root of 3. Use your cursor to get out of the cube root, and then type your minus 4. And so it's about negative 2.56. And so negative 2.56, comma 0. Okay, and so we're gonna do the same thing for example 6. Plugging in 0 for y, that means we set the entire function equal to 0. So first step would be to subtract the 4. And then now we're ready to cube root both sides. Once you've isolated the cube, you're ready to get rid of it. And so now we just have negative x minus 3 equals the cube root of negative 4. We have this negative, so we can divide by negative 1, which would make the other side of our expression negative. And then now these parentheses aren't necessary. And then our last step would be to add the 3. And so if you don't have a calculator, you would leave it in terms of the cube root, which is negative cube root of negative 4 plus 3. And so to get the decimal approximation, negative math 4, negative 4, right arrow, plus 3, 4.59. I usually keep 2. It'll be specific what to keep if you're using a calculator. And so as an ordered pair, it would be 4.59, comma 0. Okay, and so that's how you find x and y intercepts. And then now going back to example 1, they want us to identify transformations. And so we have 1, 2, 3 transformations. The first transformation is a vertical compression by 1/3. Second transformation is a right 7. And then last transformation is an up 6. Okay, and so if we're picturing this on the graph, it's still opening up to the right, down to the left, and right 7, up 6 would be our inflection point. Domain, all real numbers all the time. Range, all real numbers all the time, because of that S shape. To find the x and y intercept, we would do exactly what we just did on those other examples. So for the x-intercept, we set the function equal to 0. First step here would be to subtract 6 from both sides. And then to get rid of this 1/3, we would multiply both sides by 3, just isolating the cubed expression. And then now we cube root. And then we add the 7. Okay, and so I'm going to leave it in terms of cube root right now, just to save time. And then for the y-intercept, we plug in 0 for the x. Okay, and so that would give me 1/3 7 cubed plus 6, and then 7 cubed, or -7, sorry. That changes things, be careful. So -7 cubed is -343. 1/3 times -343 plus 6 ends up giving us the decimal 120.3 repeating. You'll likely have much nicer numbers on your test, especially if it's non-calculator. Okay, here, be careful identifying your transformations. There are no parentheses at all, so everything is happening in the vertical direction. So we have a reflection across the x-axis, we have a vertical stretch by 3, and then we have a down 7. So reflection across the x-axis, that means my slope between the middle 3 points is going to be negative. And then we have a vertical stretch by 4, and then we have a down 7. The only transformation that affects our inflection point is the down 7. So our point of symmetry would be 0, -7. Remember, the point of symmetry and the inflection point are referring to the same point. We're just calling it different things. Domain, still all real numbers all the time. And now they want us to find the max and min on this interval. So remember, when they give you an interval, those are x values, okay? And so at x equals 2 and x equals 6, because this is a decreasing function, we can imagine x equals 2. So it's helpful to know where the inflection is, but not really. You don't have to know, but 0, -7, 0 would be here, would be to the left. And so we can already kind of tell that our maximum is going to occur at x equals 2. And then our minimum is going to occur at x equals 6. Okay, so x equals 2 will give us our maximum. X equals 6 will be our minimum. It's always, your max and min for these functions are always going to occur at the end points of your intervals. So you just have to plug them in. Okay, and so if we plug in 2, we get -4 2 cubed minus 7. If we plug in the 6, we get -4 6 cubed minus 7. Okay, in this case, we get -39. In this case, we get -871. Okay, and so obviously -39 is bigger, so that's your max. And your minimum is -871. Again, the numbers are going to be a lot more reasonable for a test, or you'll have a calculator. Okay, on this next one, it's not written in proper form. It'll be written in proper form for you. And so I'm going to go ahead and just put it in proper form. And so you need those double parentheses to see the left and right whenever you have a scale factor. And so identifying 1 transformation, 2 transformation, 3 transformations. And so first transformation is a reflection across the x-axis. That means we have a decreasing function. Oops. And then this 1/2 inside is your horizontal stretch by 2. And then right 4 will affect our inflection point. So right 4 puts that inflection point at 4, 0. So point of symmetry is 4, 0. Domain, still all real numbers. Range, still all real numbers. And this time we're looking at an interval from x equals 0 to x equals 8. So x equals 0 would be to the left of this 4. X equals 8 would be to the right. But still, it's a decreasing function. So we know our maximum is going to occur at the x equals 0. And we know our minimum is going to occur at the x equals 8. Okay, and so we're going to plug those in, x equals 0, x equals 8. And then you can actually plug it into good form or bad form. And so I'm going to plug it in without the extra set of parentheses. And so negative 1/2 x minus 2 cubed, negative 1/2 x minus 2 cubed. Plugging in 0, plugging in 8. Okay, and so 1/2 of 0 is just 0, minus 2 is negative 2. Negative 2 cubed is negative 8. Negative 8 is positive 8. That's more like what you would see on a test. Okay, here 1/2 of 8 is 4. 4 minus 2 is 2. 2 cubed is 8, so we have negative 8. Okay, and so our minimum is negative 8. Our maximum is positive 8. Okay, the last thing is we are going to write the equation. So it says write the equation for g of x if g of x is formed by reflecting x cubed across the y-axis. Okay, and so that means we're going to have a negative inside our parentheses. And then we have a horizontal compression by 1/2. Go ahead and change that to a fraction, because if it's inside, if it's horizontal, it's going to be the reciprocal as the scale factor. And then we are moving left 3, which means we need a second set of parentheses. Left 3. And lastly, up 11 would put the plus 11 outside. So most important thing to remember is if you have a scale factor inside the cube, you need a second set of parentheses if you also have like a left or right translation.